So yesterday we discussed about the voltage selection, and we discussed about the nominal voltage, rated voltage. Let me open the presentation also. Yeah, so step one, when we start the engineering design process of any project. So step one, take the project and go through the scope of the work, and we discuss that how many type of the project comes in market. So like type of the client, and then we discuss about this is what is the way that we discuss yesterday. Then we discuss step number two, that how to read any tender or how to read any contractor technical specifications. So step number two, we have to collect all these document we have to collect. And when it comes to the uh, this renewable power plant project, like we can classify this discussion in two type. So the any project we can take, and we can classify that there is two kind of the project we come in a overall view. The project executed, or the project given by the government, right? And second kind of the project, that may be the government project, or we can say that is the private project. So when we work on the government project, in that case we have to read out the project technical specifications. The technical specifications we have to read out, and based on the technical specifications, based on the project requirement, we have to design the project. And plus we can refer the IEC and IEEE standards. So the project technical specifications plus IEC and IEEE standards, that is the main reference to design the project. And when it comes to any private company project, the private company project, I'm telling, like any independent power producer, which I mean from independent power producer means any wind power plant. Like if you go in Rajasthan region, there is a lot of solar park we have. If we go in Gujarat, Bhuj region, we have a lot of wind power plant. So any solar power plant, any wind power plant, any small hydro power plant, that is also done by the private companies, small hydro power plant. So when we work for any private power producer company, example this kind of the company who executing this kind of the project, in that case, to start the designing work, we have to read the design basis report. We do not get any detailed technical specifications, right? We have only brief design basis report. In that, the project brief requirement is given, design basis report. And plus we have to follow the grid regulations. I'm just telling you the method, the approach, how we will proceed for the designing of any project. The grid regulations, the country grid regulations. If we talk in India, so we have the CEA, the Central Electricity Authority, this grid regulations. So CEA, or we can follow the grid code, or we can follow the PGCIL as a reference also, or we can follow the CBIP. These are the reference manuals. So we have to follow the design basis report. We have to follow the grid regulations. Plus along with this, we will use the IEC and IEEE standards. So this IEC and IEEE standards, in the government project, the equipment requirement is given. The equipment rating is given. The equipment requirement is given. But here the equipment rating, all we have to calculate. And why the equipment rating is given? The reason that because when they are making the project, they're considering the next 30 years life and next 30-year grid expansion, grid expansion they are considering. So based on that, they are providing the equipment rating. But here they are not considering the 30 years grid requirement. They are just considering their plant capacity. I mean to say, if my solar power plant having 300 MVA capacity or 300 megawatt capacity, so considering this 300 megawatt, 300 MVA, we need to calculate the equipment rating, the equipment current ratings. and that is the only we have to fulfill. We do not need to go through that what may be next 30 years requirement. This is the grid substations that connect into the grid, and that is the power plant or generating substations. I hope this two approach is clear. So we discussed type of the project, we discussed if government project, so how we will proceed, if the private project, then how we will proceed, what should be the our approach, what should be our process for the designing. I hope this difference between these two type of the project is clear to everyone right now. Please let me know. All right, so and now now let us take this technical specifications. This one, this one because we need to understand about the technical specifications, and we are going to study that what is and one more thing, that what IEC and IEEE standard required, what IEC and IEEE standard required, that list yesterday we have discussed, right? That what is the which IEC and which IC are the IEEE standards we will follow, that we have discussed. So this list we have prepared. I think this is the list of all the IEC standards. So this standard is clear that which IEC and IEEE standard we are going to follow, right? And now we are discussing how to read the technical specifications. So when we work for any government project, so how to read the technical specifications are, because technical specification may be 200 or 300 page document. So what is the important parameters that we should have to go through, not the entire document. We can go through the important and relevant page. So the first page, the first uh, point that we have to read into technical specifications is the design criteria, the electrical design criteria, right? Electrical design criteria. In the electrical design criteria, they tell about the voltage, the nominal voltage, the rated voltage, right? And other type of the impulse voltage, then switching voltage, then power frequency over voltage, creepage distance, right? The frequency, what frequency we are going to follow. So these are my electrical design criteria, and sometimes this criteria we also called as the system parameters. And when we are making the drawings in the single line diagram, we need to mention all these things, and every equipment rating plate will have all these things in their rating plate also. So this is the discussion that we have done yesterday in the session, right? How to select the what is the nominal voltage, rated voltage, impulse voltage, switching voltage, power frequency voltage, that we have done discuss yesterday. Creepage we have not discussed yesterday. That we'll discuss when when we will come on the insulator part, or when we will come to the transmission line. In that model, we will discuss about the creepage distance calculations, and all these things we will discuss at that moment. So you can note and you can remark that later on in transmission module we will take this point. I hope this is the overall brief discussion that we have done yesterday, right? That is the brief recap of yesterday discussion. I hope this is clear to everyone. So far everyone is clear, everyone fine. Yeah, tell me if anyone facing any difficulty. Yeah, Raghunath, thank you. Let me ask one question in a layman language. Let me take this slide. So we discussed this point. We discussed this point. We discussed this point B. Then step 2, IEC standard. This all we have taken the reference of IEC standards. IEC standards. Yeah. So here we have taken that equipment have two components, the conductor and the insulation. So outer, this is the range of the voltage that exists across the world, right? And equipment view we have taken, this is some IC, and this list we have discussed a study that any equipment must satisfy this requirement: nominal voltage, rated voltage or max continuous applied voltage, power frequency voltage, lighting and switching. So equipment voltage selection, equipment insulation selection should be done based on this 5 voltage value. that we have done yesterday, and we have seen that these 5 voltage value is also mentioned in each equipment rating plate. So we have taken the reference of this transformer rating plate, and we can see here that this voltage value is mentioned on the rating plate. Let me ask one question: what is the meaning of this value in a easy and layman language? What is your understanding about this voltage in a layman language? Means the guy who is not from the engineering background, then how you will going to define this value significance in a simple layman language, in an easy language, how you can define this? What is the significance of this? What is the significance of this voltage value written in the rating plate? What is significance? Why this is important? I think I am audible to all of you right now. Even though this point we have discussed yesterday, just for your deep understanding, again I'm putting on the same point, but please do not take very much time because class time is very less and topic is very much more. So if you are not aware, tell me no, I will explain myself, but do not pause and wait that the other will reply, you are not going to reply. Equipment is protected against natural events like lightning. Uh, no, no, no. In a layman language, yes, Alice, you are almost correct, but we can make it more easy. We can make it more easy, more simple or more easy. Yeah, that is the basic instruction. That is correct. We can say that that uh, when we work in any electrical grid, so there are many disturbance that occurred in the grid, right? There are many situations that we have to face. Not the conductor insulation, that is the insulation, not the, yeah, we can say conductor insulation, but that is the insulation basically. Yeah, okay, let me explain. So in the entire service life, the equipment will face many uh, transient voltage, many type of the voltage. So we have seen, we discussed that first of all the nominal voltage that equipment will operate, the highest voltage or rated voltage when there is a rated voltage when the light load conditions, the grid or the substation or the transformer is lightly loaded or less loaded, then how much voltage that may come on the equipment. So that is the nominal and rated voltage. So this two voltage significance is clear to everyone. Now we are taking that, let me take one equipment. Let me take equipment, a site picture, site picture. Please try to connect with me, otherwise you will skip the concept. Yeah, let me take one equipment. Suppose I'm taking this equipment, this LA or the CVT. So the nominal voltage and rated voltage we have discussed, and that is clear in a simple language. Now I am telling that whenever any direct lightnings occur, even though we have provided the lightning protections, even though we have provided, but there is a chance that some lightning uh, voltage bypassed, and that may come on the equipment. So the equipment should not flash over, the equipment should not puncture, the equipment should not blast. In a simple language, equipment should not blast, equipment should withstand that lightning voltage stress without fail. Even though we in the actual life we cannot take the guarantee, but as per the lab practice we are coming with this guarantee because we have applied this much voltage in the lab by the impulse generator. So based on that we are taking the guarantee, but actually it will withstand or not withstand, no one can take the guarantee. But based on the lab we have done the testing, and after the testing we are putting putting the equipment here. So when the lightnings occur, we have seen here, when the lightnings occur, and suppose this lightnings come on the equipment directly, then equipment should not flash over. So how much voltage that may come from the lightning, as per the SIGRE, they have classified the voltage level based on the they have provided the voltage based on the rating of the equipment, because when the rating based on the rating of equipment height change. So based on the height, they have provided that how much voltage this equipment should withstand without the flashover. So that is the significance of this lightning voltage. This lightning voltage. And let me again come back to the slide. Yeah, that is the significance of this lightning impulse voltage. That equipment will not flash over. Equipment will withstand. Fourth, and this one, power fixed over voltage means if any temporary over voltage come on the equipment, then equipment again will not flash over. Equipment will withstand that temporary over voltage also without fail. And third, this one, switching impulse means if we are doing the switching of ultra high voltage or 400 kilovoltage system, then switching transient, switching surge will come on the equipment, and that equipment should withstand the switching surge voltage also. I hope that is clear. Means we are taking the guarantee that equipment will not flash over, will not puncture, will not damage, and equipment will operate. I hope this is clear. If not, please again let me know. I will go in another way, try to make it more simple. Okay, so I hope this is clear. Okay, so voltage we have discussed yesterday. Now today today agenda today agenda is the voltage selections we have done. Voltage selections we have done. So we have taken this one, and the first of all we have to read technical specifications, and we have to check the electrical design criteria, and all these value we have to check in technical specifications, and the importance that each equipment rating plate GTP must follow this requirement. That is the requirement. Now in the electrical design criteria, after the voltage and frequency, one more parameters we mention, that the short circuit rating. So today discussion about the fault current rating or short circuit rating selection. How to select the short circuit ratings, right? So before going on to this short circuit rating, let me review your homework, that what you have submitted, and then we will go to this short circuit rating or fault rating selections for the equipment. Even though this is given, but I'm just try to understand the significance, and trying try to understand that how to select these all parameters for a renewable power plant. So yes, these all ratings, these all we will select based on the IC 60071, part number 1, right now page 42 and 43, I think. Please check the part number. So when we work for any renewables, then these all we do not get in the specifications. These all value we have to select. For that we will refer this IC standards, and from that we will select all these values for the renewables power plant also. Now short circuit rating, let us understand both the difference between the grid and the renewables or solar or wind or hydropower plant, that case. So let me now, or we first discuss short circuit, thereafter we move to the assignment review. What how we should proceed. Tell me how we proceed. Let us discuss first this, then we go to the assignment review, or first we check the assignment, then we go to this short circuit rating. Okay, all right. So let us discuss the first short circuit rating. Yeah, Raghunath, I will follow you. Okay. So coming back, and please focus, because in the entire class we will take this short circuit rating. So you might miss that how this value comes, So this class is the reference for all the short circuit ratings value that we are going to use in the entire class, right? So please give me your 1 hour about the short circuit ratings, selection and the discussion and the understanding. Voltage is clear to everyone, I hope so. Let let me take first this one, government any tender. Let me go to as per the tender first. So when we go to the tender, let me open the tender technical specifications that is given by the client to the contractor. So yeah, here this is the electrical design criteria table. So we can see the voltage, max operating, nominal, rated, frequency, phase. This already we have discussed. And now correct creepage distance not discussed, so that is the that we will discuss later on. Later on. Voltage and current first. Let us complete. And this point is important for now discussion. Fault current rating. And the fault durations. This one. Fault current rating and the fault durations. Yeah. So as if we are working for this project, for this grid project, in that case there is no any calculations, we have to select directly the fault rating as per this table. For 33 25, for 132 kV 40 kiloampere, for 220 50 kiloampere, and for 400 kV 63 kiloampere. This value we will directly take. And 1 second, 1 second, 1 second, and 3 second. For 3 second, I will come with the explanation that why 3 second is mentioned here, why not 1 second mentioned here, based on the relay based on the relay coordinations concept. Just wanted to take print out this one. Yes, okay. Okay, so grid case of the project, this is clear. So whenever you work in project, you need to select this one rating because this is given every time. What is the concept behind this? What is the concept behind this? Actually, when we work for any substations, when we work, let I have prepared some write up also. So rated normal current and fault or short circuit current label selection for utility grid substations. So since the utility substation plant expected life is 35 years, therefore equipment normal current, and here we are discussing two parameters, not only the fault current, the normal current also. Why? Because if you see this fault current and the normal current also written, normal current is also given in this tender. You can see here equipment and facility. The switchgear shall be designed to withstand operating conditions and duty requirements. The equipment shall be designed considering the transmission line capacity: bus bar 4000, line by 3150 ampere, 220, 3000, 1600. So ampere rating is also given. So two point we are discussing, not only the fault, the current rating selections, the current rating I, and plus the fault current rating or short circuit current rating that we can put as the ISC. So case one we are taking case one we are taking for any government type project. So utility substation is plant expected life 35 years. Therefore equipment normal current and fault current selection should be consider the future load growth. Means means when they are planning the substation transformer rating and the equipment rating, the grid substation, the client or the government electricity board will not take the only current load. They will take the next 35 years load, and in the next 35 years the number of generators solar generator, wind generator, the power plant, thermal power plant generator, nuclear generator, this all will contribute. So they will also add contribute the fault, and the load will also increase. So considering the past 10 year or 5 year load growth requirement, they the grid transmission planning department planned to the next 5 years and next 10 year or next 30 years load with considering some margin also. So that is why when they open any uh, tender, in the tender they always mention what should be the equipment current rating. This is the statement number one. Second statement, as per the electricity grid rule, let me open that grid rule also. Let me open that grid rule also. uh, Let me open the electricity grid regulations. So standard, this is the CEA, right? Is as you can see here, this Central Electricity Authority, Ministry of Power, Government of India. Every country have their own grid regulations. Coming on to the substation point, because yeah, coming on to the substation part, chapter 4, technical standard for the construction of substation and switch act. Okay, see, and let me come first to the current rating. The current rating. Yes, the current rated current. Rated normal current of switchgear CB rated, this shall normally be H indicated here. Indicated here. Let me take, yeah. This is first of this statement. The substation or switch yard shall be designed and constructed to give a life of not less than 20. Initially it was 25. Now the grid have modified and they have given the 35 years requirement. So as per the grid regulations also, we have to design for next 35 years. So as a contractor, because we are not aware about all the grid right now, we are not aware about all the grid, how much the total number of generators, how much total number of loads, we are not aware. The EPC contractor, that is aware, controlled by the transmission planning department of the grid. So they are aware about their grid, the grid, the grid company. So they will plan for the next 35 years, and based on that they will provide the current rating, that what should be selected, considering the future growth also. And similarly the current rating and the fault current rating, the rated rupturing capacity of circuit breaker to be installed, this. So for every voltage there is a fault rating given. For 66, 31.5, 132, this one same, 220 initially 40, now 50, 400 initially 50, now 63, 765 kV, this one, 1150 kV, this one. So what I trying to explain, that when we work for the grid, let me open if I have any grid network. This is an example of the grid generator, then transmission, then this substation, right? And this substation, this one and this one. So maybe there may be some more industry, there may be some more industry coming. So in that case the current requirement will increase. If more generator we are adding, so generator will also contribute to fault current. So this total grid will also consider next 35 years industrial development, the generator development, and based on that they will suggest the equipment rating. What happens in a few of the project which we are doing, that they are the old substation and they are not designed for the higher grid fault rating. So the government now opening the tender to replace the existing substations equipment, and they are planning, they are doing the extension. So they are putting the new equipment ratings, the that having the higher fault ratings, higher fault capacity and higher current rating capacities, right? The old substation, that is 35 years or 25 years old substations. So that also we need to do in few project. I hope this point is clear, that how to select the grid fault rating. So we will not calculate. First of all, we will follow as per the project. And suppose if we are working for any renewables, this one, in that case, since when we are making the solar, let me take any solar power plant, any solar facility, if I have at present ongoing project, solar hero future, this facility have not, yeah, this one facility, that is again 300 MVA solar power plant, that is done by the hero future. Hero future means that is the private company right now. That is the uh, this one, project 375 megawatt peak, key single line diagram, clean solar power Jodhpur. This is the developer. Clean solar power Jodhpur. This is the private company. They are generating the 300 megawatt power. And now you see, after the generation, this is their evacuation line, 220 kV transmission line. This is the plant end, and now you can see there is a transmission line here. This is the HFE plant. It means the Hero Future Energy plant end, and now they're connecting through help of the transmission line. This line is in representing the transmission line to the power grid service station. So they are making 300 megawatt power, and they're feeding to the again power grid PGCIL service stations. It means these all equipment rating, since it is connected with the grid, so these all equipment current rating, fault ratings should be as per the grid, right? Because if the fault happens here, the grid also will contribute the fault right now. And if equipment is not designed for that fault current rating, for the grid fault current rating, then equipment may flash over. Is that making some sense or not? Is it making sense? Please share. If you are not agree, say no. I'll come with the next another point. But do not wait. Time is again, I'm telling, important. And please active on the chat box. Yeah, Rohit. Now clear. Yeah, Kamis. Okay. So one thing is clear. One point is clear: when we work for any grid, whether it is government, whether it is renewables, in that case, the short circuit rating, we will follow as per the grid regulations, so what I mean to say, for the government project, this value is given in the tender, but for the renewables we do not have this much technical specification. In that case, we will follow the electricity regulations, CEA. That is this is the copy of the CEA. Right now, this is the copy of the CEA. So based on that, I will select the equipment fault rating, considering this grid regulations fault current level value. Hope this is clear to everyone. So the fault current rating selections is clear. Okay. Now when it comes to the current rating, so current rating is given in the technical specifications, in the government technical specifications, but here the current rating will not be given, because the current rating is depend on the voltage and power, how much we are going to evacuate. So in this case, in this renewables case, the current rating we will calculate based on the formula, right? So let me take that project again. Let us see the fault rating, and this, yeah, you can see here wave trap 40 kiloampere, because 220 kV to 40 kiloampere they have to take. Now the wave trap, this 1600 they have taken. Okay, and then CT 800 500 they have taken. So this all equipment current rating we will calculate considering the formula: 245 kV 1250 ampere isolator, breaker 1250 again, right? So for that we will discuss in the next module, equipment selection and sizing calculations. So here I will discuss the sizing, the current rating calculations. right? Fault rating, today we are going to freeze the fault rating value. So this is the one approach, one understanding when we work for any uh, grid substations. Now let me come, if we work for any industry, any mill, right? Any industry, any industry, any kind of the industry. So what happens in any plant, any industrial setup, any industry, have to, they can generate the power, right? Or they will take the power from the state electricity board, and they will feed to the transformer, right? And then suppose they are taking 11 kilovoltage from the electricity board, and then step down to 433 or 415.433 kilovoltage, and then this 433 kilovoltage they feed to the power distribution panels, and from where they feed, right? And there might be some case that they take 11 kilovoltage, they take 11 kilovoltage or 33 kilovoltage step down, and then they feed. There might be 2 or 3 voltage level also here. So this is a small industry, small any building, high rise building, or any small industry, they take like that 1133 step down, and then they feed. In that case how to select the fault rating of equipment. So this incomer side, 11 or 33 kilovoltage side, whatever we are taking from the board, we will go as per the board, as per this electricity board. So we'll take that for 33 kilovoltage, or for 11 kilovoltage, what is the grid, as per the grid, what is the fault rating recommendations, and it is generally 25 kiloampere or 33 kiloampere or 31.5 kiloampere. So based on that we will select the HV incomer fault rating, considering the electricity board fault rating. But when it comes to the LV, and we have the transformer, and transformer is insulating, because in the transformer there is a insulation between the HV and LV. No electrical connections, no indirect electrical connections, only the magnetic coupling. Here we have the magnetic coupling. In that case, this side of the fault rating, this bus fault rating or this fault rating, will be decided based on the fault rating of this transformer, that how much the fault current this transformer will contribute on their terminal, and here, and based on that we can select all the switchgear fault rating. So in that case, we will not go to the grid. We will calculate the fault current value as per the transformer voltage, power, and the impedance value. So for that calculations, we can take it. We can take the ETAP. We can take the ETAP, and then we can perform the calculations. Okay. So let us go to the ETAP and open any reference, any project. How to work on the ETAP intro I have already given to all of you. So I hope that everyone aware how to, what I'm trying to do. Now let me take any system. Let me draw any system here. Any SLD. Any SLD. Let me calculate. So this is my electricity board here, and then this I'm feeding to one bus, and then we have one transformer, step down transformer, then again we have LV side bus, right? And let me connect this, and already we have discussed that this power grid we use as electricity board, right? So this is my electricity board, and I'm taking supply here, and then we can put some, let me put some breaker also. So high voltage circuit breaker, or we can take any low voltage circuit breaker, so we can put any switch here also here. Okay, and then we can draw any load. We can, okay, let us take the full fault current that may come on this first, and that fault rating we can take for the entire plant. So suppose this incomer is 11 kilovoltage, supporting the 11 kilovoltage bus rating. Incomer, this 11 kilovoltage short circuit rating, So X by R I am putting 14. That is the one rule, that X by R for a 50 Hz system we take as 14. Why 14? I will calculate and then I will perform in the ETAP module. And if 60 Hz system, then X by R we take as 17. But at present you remember, but I will calculate later on about this value, right? 25, suppose 25 kiloampere is the grid electricity board fault rating that I am currently assuming. That we can discuss with the electricity board and we will get the exact data. But generally 25 kilovolt is come. Then we go to the transformer and click on here, and then it comes to the rating. X by R will come, Vignesh, don't worry. What is the X by R? Why X by R? How to calculate the X by R? This all we will discuss in the detail. So I'm not going into the ETAP discusses at present, Vignesh. Let me go with the fault current calculations only at present. X by R, please you note down. We will discuss in the ETAP module. Okay. Because X by R is again 1 hour discussions. So I am not diverting this discussions toward the X by R. X by R is the ratio of reactance and resistance that we can see here. Value, as I said, the value of X by R, for any 50 Hz 50 Hz system, the X by R is value is 14. So please remember this value. If 60 Hz, then it comes as the 17. You don't worry. I will calculate this value in my next module. When I will come on the equipment calculation, then I will calculate this value. Okay. So because it is again 1 hour discussion and we will divert from the fault rating discussion. So let us note down. We will calculate and we will prove this value later on. Okay, going to back. And let me ask one question. For a 11 by 415 system, what should be the maximum transformer power rating? What should I put? 33 kV voltage they have taken, and secondary voltage let me put as the 415 right now. 0.415 my secondary voltage. Click OK. So when I am going to the transformer and coming to the rating plate, the primary voltage 33, secondary voltage how much? 433 we can take, right? This is the voltage rating. Okay. Now my question is that how much power rating we can take for this kind of the service, this kind of the industrial plant? How much power rating of this transformer we can take? It is possible. It is not by the industrial load, but there is some electrical limitations also. Okay. If their load is increasing, then they do not take the 11 kilovoltage. They will take 33, step down to 11. Some load will connect on 11 kilovoltage, and then some load will connect on 433 voltage. So if in that case, any LT transformer that have, the question is that now let me tell in a separate way, any LT transformer that have the 11 kilovoltage as the incomer, secondary side 415 voltage or 433 voltage. So what may be the maximum power rating of this transformer that is possible to select? As a design engineer, how much value you are going to suggest? No, 63 kVA. Why 63 kVA? Let us see. And let us try to understand. Let me go to the 15 MVA now at present. This is by default it is given 15 MVA. Yes, correct. 15 MVA. So when I putting the 15 MVA power, in that case, what is the FLA stand for the full load ampere? What is the FLA of the primary side of the transformer and the secondary side of the transformer? That we can see here. The primary is 262.4. The primary is less. That is not a problem. But yes, secondary side full load current is 20 kiloampere, and this much switchgear is not available in the market. For sure 15 MVA, if we select We cannot arrange the switchgear from the market. Okay, so 15 MBA we cannot take, right? So what we can take? Yes, mostly generally that we take. I have received some correct reply also. Yes, 2.5 or 5000 kV. Correct, Sanket. 500 or 2.5 MBA. Generally we go with the 2.5 or 3 MBA. Let us take 3 MBA. Then let us see the value. 3 MBA or 3000 kVA. Let us see the value. Yeah. If we put 3 MBA, in that case, the primary FLA is 52.4 and that is very less. Secondary current, that is the main concern, it is 4000 ampere. I think the 4000 ampere circuit breaker is available in the market, that we can purchase from the vendor. Few manufacturers is making the 4000 ampere rating, right or not? So if we go with the 2.5 MB, then 3300 MBA. So generally the max to max rating that we can take, if we go to the 5 MBA, then how much? 6667. I don't think 6667 ampere rating breaker is available. I think the maximum breaker rating available is 36300 right now. You can see the catalog, the market availability, and based on that you can select. If 6667 is available, then we can go to the 6667. Otherwise, we can go around 3 MBA or 4 MBA. 4 MBA, yes, 5000 ampere is available. So yeah, the point is clear. The concept is clear. If this much current rating available, we can go with the 4 MBA. If any vendors ready to supply to the 6667, then we can go to this one. But as per my knowledge, 6667 or 7000 ampere breaker is not available in the market for the 433 voltage. What is the formula? What is the formula here? Tell me the formula. Let me ask you. Let me ask other. What is the formula? What formula we can apply if not using the ETAP then? Okay, I'll tell you the formula here. No, no, Raghunath. No, 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 no. Not P is equals to VI. We are not in the DC system, Raghunath. P is equals to VI. What? Yeah. See, let me tell the formula then. Power factor, no power factor, Raghunath, no power factor. Let me tell. No power factor at all. Let me tell overall concept. So the power have the two unit. One unit is the kilowatt or the watt or the kilowatt we can say, or megawatt we can say, anything's kilowatt or megawatt. Our power have that second unit, that is the kVA, maybe VA also, kVA or MVA. It means there is a two kind of the unit. One is the load, this is the load, and this is the source. So there is a two type of the electrical system, load and the source, right? If we have the load, then we represent into the kilowatt or megawatt. If we have the source, then we represent into the kV or MVA. For example, any trafo rating, the dg rating that also comes into the VA or kVA right now. QPS rating, so this all is the source of the power. So the source rating comes into the kVA or MVA, the load rating comes into the kilowatt or MVA into megawatt. So when we present the load into the kilowatt or megawatt, in that case the power formula we will follow for a three-phase system under root 3 into V into I into cos phi, and cos phi value generally we take as 0.8. So we will follow this formula for any load system. But when it comes to the source, then the power formula will not be like this. Power formula simply for a three-phase system, P is equals to root 3 into V into Y. That's it. No any power factor will come here. And I think we know the formula also, kVA and kilowatt. That we can do. That we can do, Salis. Uh, one second. Okay, yeah. Ganesh, are you there? Ganesh, please unmute yourself. Ganesh. Okay, so anyway, this is the formula that we are going to apply. So we know the power, that is 2.5 MVA. Okay, 2.5 MVA into 1000 comes to the kVA under 3 into V, that is also in 0.433 kV, right, into the I. So we wanted to calculate I, we can calculate. Okay, by solving this formula. Ganesh, okay, so this is clear. This is clear to everyone. Okay, now, yeah, coming back to the ETAP again. So yeah, 2.5 MVA, this much we can take, right? Formula also discuss, and then go to the impedance tab. Now how to set the impedance, that we'll discuss later on. But let me go with the typical Z and X by R. Typical Z, typical impedance, again typical X by R. So how to calculate the X by R, I will explain into the ETAP module. But at present, I'm going to the typical X by R, typical X by R of the transformer, right? And then putting delta, primary delta, secondary other star, and yes, we can go with the solid. We can see the symbols also here, and then click on the OK, right? And thereafter we can perform the short circuit analysis. Now go to this tab of the E tab, click here, and then see what is the current rating. So let me click on the duty. There might be bus 42, T16, and short circuit. Bus 42 is here. T16, where is the T16? What was the fault current? Okay, let me produce the fault here. Then tell me. Bus 42 and T16 base kV. T16. Let me check here the rating, and what is this rating? 0.4. That is okay. 0.433. Yeah, that is fine. Let me take 0.415. Okay, click OK, and then go to this.
Your primary voltage on the transformer is 33.
Oh, that is the mistake. That is the mistake, because here we have taken 11 kilovoltage right now. Oh, that is the that is, it is coming like here. Okay, 11. Yes, that is the mistake. Yeah, 11 kV bus, but we have put here 33. That is what is showing there. Okay, now we corrected this, and let me know now. Go to the fault rating. Yeah. So what is the fault rating that we can see here? That is 58.1 kiloampere. Three-phase fault. What is the fault that we have taken here? Short circuit 25. Okay, what the vector group that we have taken here? Rating 11. This is then impedance. Okay, grounding, delta star, solid. Okay, click OK. So 58.1 fault current that we will select. Now let me take one just give me 1 second. I think I have some reference standard on this. Yeah, so this is one CBIP manuals. Again, this manual is about the LT system, and going to this, going to this. This is as per this recommendations. Yeah, as per this recommendations. Yes, you can see here section 10 6.6 only 433 voltage auxiliary supply distribution transformer. So this is our case. This is our case. This is one standard I am taking as a reference. Okay, because if I tell anything that should be supported by the standards only. So what I am telling here, what we can see here, the impedance value of the transformer shall be so chosen as to limit the fault current level of the 415 voltage system, preferably to 36 kilovoltage. Where that requirement is not possible, a fault current rating 45 kiloamperes shall be adopted. So as per the CBIP recommendations, uh, this one, they are telling that anyway. So first of all, let me go with the without standards. So what should be my fault rating here? That should be 58 kiloampere, right? That should be 58.1 kiloampere that we can take. So my this circuit breaker should be designed for this 58, or we can take some margin, we can go with the 60 kiloampere. So my this circuit breaker should be designed based on the 60 kiloampere or 58.1 what we just calculated. So in this case I will not follow the grid. In this industrial case, we will calculate the fault rating from the calculations by manually or by the ETAP software. I hope this point is clear to everyone. So please let me know overall, in the overall view, the grid system, the renewables power plant, and any typical industry, fault rating is clear to everyone or not. First is this point, right? Yeah. Second point, I just wanted to add one more statement. As per this manual, when we read this manual, we found that for the LT system, the fault current rating should not be more than 45 kiloampere. Now, how I can modify the fault rating, because my trafo rating is 2.5. So how I can modify the fault rating, that how I can reduce my fault rating from 60 kiloampere to 45 kiloampere. For that, I can go to ETAP and I can go to the trafo, and I can play with the transformer impedance. So in place of 6.25, that is the default impedance, I can increase this impedance around 8 or 10 kiloamperes. Let me increase, because if impedance increase, if Z increase, then current will reduce. Okay, so let me increase to the from 6 to 10, and then let me again perform the calculations. Yeah, yeah, that we can see 38.3, so that is very much less. So we can again go to the 8 and sorry, not 88, 8 and 8, and click OK. Click 46.7. Yeah, 46.7. The switchgear is 50 kiloampere switchgear is easily available in the market right now. So I can play with this impedance, and in place of 6.25, that is the by default impedance, I can go with the higher impedance rating, 8% impedance rating. So that is the importance to do the short circuit rating, uh, to do the short circuit analysis study for any project. We decide the impedance of the transformer here based on the ETAP study, right? So I hope this is clear. This is clear to everyone. Please let me know overall view of your fault rating understanding, the fault rating selections. Yeah, and then we'll close, and then we'll go to the next point. I was just wanted to show one of my project experience in which we do same kind of the modification in the transformer impedance. Okay, let me take the CBIP. Let me take the IC also. First of all, just give me 1 second. Just wanted to show some standards to all of you. CBIP. Okay, this is again manual on the transformer that I will share when I will come on the transformer. Do not ask now. Okay, and then we go to the trafo impedance. Trafo impedance value as per the standard. Okay, where is that trafo? Yeah, the LT trafo. 422 page document. Yeah, that is 100 kV. So my case is not 100 kVA. My case is around 200, 2000 kVA. Yeah, 11 by 250, not 11 by 415 is my case. So yeah, this is the three-phase distributed trafo above the 100 kV and up to 33 kV class. So as per the standard, what should be the impedance rating? First of all, just I wanted to show you this rating. Yeah, so the impedance, yeah, correct. So you can see here for any 2.5 MVA trafo, the impedance rating as per the standard it should be 6.25 right now. And this ETAP by default have taken 6.25 percentage initially. Agree or not agree? You, I just because I have changed now. I don't think you remember or not remember. Okay, so let me go to 3000. Initially it was 6.25 right now. Uh, okay, so why the 6.25? Because ETAP have taken directly this value as per the standards of the transformer. So I showing you is the standards of the transformer here, 6.25. Now I am diverting from the standard because to meet out the fault current, to reduce the fault current rating. Otherwise what will happen, the switchgear cost will increase, the earthing cost will increase, each equipment cost going to increase if we have the more transformer, more fault rating. So what I did, in place of 6.25 we go to the higher fault rating, and when I go to the 8 percentage, then this fault rating from 58 reduced to 45 kiloampere. So what I did in one of my project, let me close this. Yeah, this is one generating power plant, that is the 15 megawatt, I think. How much megawatt? Captive power plant, I think this is 15 megawatt power plant. uh, this 15 megawatt power plant. Here we have the generator that we are generating 11 kilovoltage, then we are feeding to generator transformer. This 11 kilovoltage we are taking and then feeding to 11 kilovoltage panel here, and then this 11 kilovoltage we are taking again, and then we are feeding to one distribution transformer for the lower distributions to the industry. And you see here 11 by 433 kilovoltage, this delta star, and the rating is, this rating was around 3000 kVA rating that we have taken. The kVA is not mentioned here, but it was 3000 ampere, 3000 kVA. Okay, so for 3000 kVA, the impedance rating as per the standard it should be how much? 6.25 right now. 6.25, right? 6.25 it should be. Let us go to the 3 MVA, 3 MB, and then go to the percentage. Yes, typical. You see 6.25 right now. Typical as per the IC 6.25. That matching 6.25, right? So when you perform the calculations taking 6.25, then click on the OK, and the fault current it was coming 70 kiloampere, which was not acceptable, right? Very much fault current. So what I did here, in place of taking this value as per the standard, we have taken this 10 percentage impedance here. So if I take 10 percentage impedance, so what is the impact? Let me go to the now 10 percentage. See 10, put here 10, again put here 10, and then no, do not click here now here, because we are not going on the typical IC value. I am going as per my modified value. Click OK, and then again perform on the short circuit duty calculus. Now you can see this value reduced to 45.54 kiloampere. So we can take any 45 or 50 kiloampere switchgear and we can install it here, right? I hope this is clear. And how we can play with the impedance. What is the this manuals impedance as per this manual. what should be the fault rating value as per the CBIP recommendations, and how to calculate and how to select, right? Even though this is not the finish, even though we have one detailed session on the fault current, so here I will take generator, different generators, different type load motor, any motor type load, any VFD, or any inverter, solar inverter, and then I will calculate the fault current manually and the ETAP also. But how to take the fault current rating, what is the reference, how we will proceed, that we will take this one. Yeah, is that okay? Yeah, we can do these modifications frequently, provided your equipment vendor max rating. No, this is not Celis. I don't think they are telling. Let us see, because that is linked with the market switchgear availability. Let us see here. The preferred capacity of auxiliary trafo is thermal power station, 630 kVA, 1000 kVA, 1600 kVA, and 200 kVA. So they are telling only 2 MVA rating, but yes, we can go to the more than 2 MVA also. The star connected secondary 433 voltage with a star point plot on neutral. So they are telling us the 433 voltage that they are telling. Okay, and they are telling trafo rating more as the 200 kVA, but more than 200 kVA to 300 kVA also we can go, because the switchgear is available in the market. That is the reason. Okay, Salis. Yeah. So okay, please now let me know everything is. It is not fair. It is not fair, but in that case we have to take approval from the client, and and we have to prove that if we are deviating, so how much we are cost saving, and again if we are deviating, so I'm not deviating as per my choice, I am deviating with taking this CBIP as a reference. Okay, Mehul, right now we play with the impedance. Now we play with the impedance. We have seen, if we increase the impedance, then fault rating will decrease. If we decrease the impedance, then fault rating will increase. That is because we know that I and Z both are vice versa. Cost of the switchgear will not increase, the cost of trafo will increase only. Okay, Rohit, but not all the switchgears. I said fault rating we will we will discuss in this chapter, and manually how we can calculate the current divided by percentage impedance. The current divided by percentage impedance, that is the manual calculations for the fault rating. Okay, that we can discuss with the OEM, Sanket. That we can discuss with the OEM, that how much impedance they can tolerate. So that we can discuss with the OEM, and by consulting the OEM we can recommend. Salis, let us go with point wise point. We'll come on that point later on. I'm telling short circuit is not over from my side. I'm just telling you the method of the grid, because I will follow the grid only here. But when we work in industry, then not follow the grid. That was my concern. We will calculate. And how to calculate? I have given one example here, and we will calculate again by taking if generator, wind turbine, PV cells, VFD motor, all these things we will discuss in the detail. But yeah, So the point is that let me conclude this discussion. Let me conclude the discussion. For the grid, for the grid, for the grid, follow the grid regulations. Follow the regulations of electricity rule. And for the industry, for any mill, for any small industry, short circuit, do not follow the grid. Calculate based on the transformer percentage impedance and the ampere and the voltage what we are applied. Okay, that is the overall one line conclusion, but I do not wanted to say this conclusion without doing some calculations, without performing some calculations. I do not wanted to deliver this statement. So to prove this statement, I just perform this much exercise. Okay. Yeah. So that is done from my side. We discuss about the voltage, the impulse voltage, and the current rating and the fault current rating selections. This is the first step when we start the designing. So first decide the voltage rating designing selections are current rating, fault current rating selections. Okay. Uh, so that is done from my side. And then step number four, what how to read any tender project specifications. Step one is done. Step one was, what was the step one? Step one is the go check the scope of the work. Step two, what was the, take the technical specifications, read the technical specifications, collect all the grid regulations, this all data you ask to your project team. Regulations, take, have the all IC and IEEE standards, IC and IEEE standards, IC and IEEE standards. Step 3, what we discussed, we have to read out the uh, this electrical design criteria. In electrical design criteria, there is several parameters that we discussed from yesterday and till today, like voltage, impulse voltage, fault current, this selection. Then step number 4, we have to read in the tender about the site environmental condition, that what is the site environmental condition is given, and all the equipment should be suitable for that site. What is the switching scheme, what I mean to switching scheme, let me go to the tender again. And if you see here, there is switching scheme also mentioned. Yeah, this switching scheme, this statement, switching scheme. It is essential that the system should remain secured even under condition of major equipment or bus power failure. Substation being the main connection point have large influence on the security of the system as a whole. The selection of the bus switching scheme is governed by the various technical and other related factors. 1.5 breaker scheme for 400 kV system, double main and transfer for the 220 kV system, single main and transfer for 132 kV system, single main and transfer 33 kV system. These all things. So here is the table. So we have to read out the switching scheme, that what is the switching scheme given in that project. What I mean to switching scheme, that I will explain in my syllabus in the module number 4. Module number 4, we have the switching scheme, selection of bus bars schemes for substations. So all the switching schemes that mentioned in the tender, that I have mentioned in the syllabus also. So we'll discuss switching scheme study. At that point, the meaning significance of switching scheme will be clear to everyone. Okay. So if it is not clear, don't worry, we will discuss in the detail. So environmental conditions switching scheme, we have to read out the minimum clearances distance. Distance means the face to face clearances, the face to earth clearances. This all distance we have to read, that how much clearances we have to follow. And if we are working for the renewables, we do not have the given value in the tender. In that case, we will follow the IEC 61936 part number 1 for any renewables, solar, wind, hydropower plant. So that we have to read out. Then we have to read the current the current ratings, what is given in the standard that we have seen today also. Then selection and high voltage equipment technical particulars. And then we have to read out that every tender the equipment specifications is also given. As you can see here, for the trafo, there is a detailed specifications. Power trafo cell, confirm this one, and then this all specifications we have to read out, and this the technical parameters. So we have to read that what is the equipment type and equipment rating, equipment specifications have been asked in that tender. Okay, have been asked in that tender. And if we work for any renewables, in that case we do not have this much rating. In that case we will go as per the grid regulations. So this all we can refer to the CEA. In the CEA also we have all these ratings. Okay, let me check if I have the CEA. Otherwise I will forward the CEA to all of you. The CEA, in that this original CEA, present I do not have, but yeah, I have in my another laptop. Then I will forward. Okay, so we will go as per the CEA in that case. Okay, then we have to read out the protection and control requirement of that project. We have to check the power line carrier communication requirement. What is meaning? We will explain we will discuss in the detail. Then we have to see the firefighting system requirement. What is the firefighting system? There is two kind of firefighting system we take. The HVSW, the high velocity water system, or we take as the nitrogen injection, NFPS. So we have to see that what is the firefighting system the project have been asked. The cable details, the cable specifications, the lighting and small power system specifications, the DC power system requirement, DC voltage 110 voltage or 220 voltage requirement. So this all we have to read in the tender. Then auxiliary trafo ratings and the requirement, and along with this all specifications we have to read, and then we have to read also if there is any pre-bid queries reply by the client. So all this data we have to read. And why this data is important, let me take one example. If I'm going to the site environmental conditions, let me go to this trafo here. Let me go to this trafo here, and let us not perform the short circuit. Let us go just see the trafo performance based on the environmental conditions. So just coming on the ratings, here we can see the primary, secondary and power, right? And here we can see my installation height, that is 1000 meter, and ambient temperature 30 degrees Celsius. If I change my installation height, altitude here, let me do, and then what is the power rating? 3 MVA rating, and then derated is 3 MVA. There is no derating happens. Percentage derating how much? 0% right now. So this trafo is designed for this conditions. If I change my equipment installation height, 1000 meter, this 1000 meter, this is the height from the sea level, right? Now that is called as the MSL, mean sea level height. Are you okay? What is the mean of altitude? Altitude means installation height from the sea level. Every height is measured from the sea level. I mean to say, if you are taking the Everest height, so what is the reference of Everest height? That is the sea height. Sea level is the Everest, is the reference, and that is why we are telling height, insertion height, as we always say, that is the MSL. That is called as the MSL, mean sea level height. So here we can see, here we have any sea, and if you see, if you go to any railway platform, every railway platform have mentioned their height from the sea level, that how much height of that platform from the sea level, and based on that the entire traction system is designed, right? So if I change this installation height, that is 1000 meter, but if I go to any hilly area, hilly terrain, and if we change this altitude, then what will the impact on the transformer? Let us see. So if I change this altitude, in place of 1000 meter, let me increase just 100 meter, not more than 100 meter. Just let me increase to 100 meter more from the sea level. So what is the impact? Let us see the impact. Yeah, click outside. Yes, we can see how much. The 3 MVA transformer will deliver only 2.94 MVA power. There is a 2% derating occurs here, right? I think ETAP is the best tool to support my statement. Otherwise, if I say without this simulations, you may trust or you may not trust. But here we can see that if I increase my height from 100 meter to 100 meter, 100 meter, So each 100 meter will rate the 2% of the equipment performance. Rated is 3 MBA, but the power that they will deliver is 2.94 MBA only. Right. So generally, the thumb rule is that every 100 meter, 2% equipment rating is reduced. That is the thumb rule that we can say. So we can have a feel that why to read this. Not only the electrical parameters, the site environmental condition is also important right now. The site derating means the equipment performance is decreased here. I think I have some slide here also. Yeah. Since the occupied area of substation, since the occupied area of the substation is typically large, therefore the design of a substation and equipment selection must consider not only the electrical parameters but also the environmental conditions where the substation is exposed. And following condition is important: the pollution level, seismic level, altitude above sea level, at mean sea level, ambient air temperature, humidity, thunderstorm days per year, rainfall, designed wind speed, snow load. These all parameters we have to read out. We have to see. So this is my installation site picture that I have taken. But this site, all the details we have to take from the client, and when we review the equipment, we have to ask to the equipment supplier that this equipment should withstand not only the voltage and current and the fault current, that should withstand all these environmental conditions also. That confirmation from the equipment supplier is also important. So please also take confirmations from the equipment vendor when you are working as a design engineer. See, send your site as this conditions. I think they have given in the tender. If not, then you ask from your equipment supplier, the client, that let us know the site conditions, and takes that site conditions and take the confirmation from the equipment supplier. Okay. Yeah. How much chance of the, what we can say, earthquake? There is no any formula to it. Yeah. This is all value we have to take. All value we have to take from the client, and we have to ask vendor supplier that this also withstand. And if equipment rating is this much, then this here we have to consider 2% more margin. So in place of 3 MBA rating, I will go with the 3.6 how much, 3.6 MBA rating right now. So here we can apply some formula. Okay, so through that data we can understand. Now let me do one more change. Let me put back to the 1000 meter the installation height. Coming to the temperature, ambient temperature 30 degree is at present. If I change the ambient temperature in place of 30 to 40 degree, what will happen? Let us see the result. If I change my ambient temperature in place of 30 to 40, then what is the result? Yeah, a huge change, a huge change. 9.6% the rating occurs. Every 1 degree increase in temperature reduce 1% equipment performance. That was the statement. No admit, we have to take discuss with the equipment supplier only. They will calculate during their designing. Equipment vendor or trafo vendor will do that. But here with help of eta we can perform. We do not have any manual calculation, but yes, through eta we can perform. So take eta to it and then perform this. Okay. Yeah. Yeah, let me do if I, in place of 3, if I put 3.6, it will again de-raise as per this. Now 3.6, 10% decrease, then 3.256 is the value. Yeah, so what is my important conclusion? In conclusion, What is my important conclusion here? When you are review the equipment drawing, when as a engineer you are review the equipment rating, this rating plate, the technical data sheet, please focus on the altitude what they have mentioned, and please check that altitude from your project altitude, and please check what the current rating or the power rating on which ambient temperature they have mentioned, and that value should be as per your projected ambient temperature. So please check the temperature against that current value or the power value. Is that clear? Or let me show you some GTP, then it will be exactly clear what I'm trying to say. Any GTP that I have or not. Equipment, equipment, and then trafo. Where is the GTP? See what happens to check all a lot of documents and to, yeah, here we have the GTP. Yeah, so we can open. Let me delete the approval stamp. Yeah, guaranteed. See here, Mehul, you ask me again. GTP means, note down this value. GTP. Okay, Mehul, clear? What is GTP? Height place. I'll come on that, Ignis. Don't worry. Don't worry. Yeah. So coming back, coming. Let us first let us see the temperature. So what I need to check, not only check this much. Okay. So let us see. Let us check the GTP. This top of GTP. Okay. Rated power this much, 150 MVA. 150 MB, and then this HB, this power. Okay, then voltage 3 220 33 kilo voltage. Okay, and then percentage voltage version 50 has number of phase, 3 phase, HV current, LV current. Okay, then this, yeah, you can see 40 40. And let me see if any other temperature they have mentioned here. Yes, ambient peak temperature specified. This is the point that I wanted to highlight. Ambient peak temperature specified 50 degrees Celsius. Means this equipment is designed for 50 degrees Celsius operations. Okay, so do not ignore the temperature. Always see the temperature. That is the conclusion. Okay, now what happens? What happens? Coming back to how the height changing the this value. That is your point, right, Vignesh? That is your point. Let me come back to 30. Now ETAP is taking 30, but yeah, what will happen when we go above to the sea level. uh, when we go, this is my sea level or ground level or sea level, as you can see. When we go above uh, to the sea level, so what will happen, and when you travel to flight, you can see if the air pressure is reduced, then take the breathing like now, means the air pressure is reduced here, the air density is reduced, air density is reduced, air density is less. So what happens between two equipment, in case of AIS, air insulated surface stations, what is the insulating medium? That is the air. Am I correct or not? And air is the insulator, and suppose this air density is less or insulator density is less, reduced, then what will happen? The proper clearances we are not able to meet out between two equipment. Okay, proper clearance is not able to meet out here if the air as insulating medium and their density, their weight is reduced in that case. So when we consider the uh, rating equipment rating, and since this air density is reduced. So the insulating medium that insulating this equipment to this equipment is less. So whatever the clearance is required, or whatever the flashover, that may go directly to this equipment also, that may go to this equipment also. And if one more point, if my air, because whatever the heat this conductor is eliminating, this radiate this heat, whatever the heat this equipment is generating, so air is only air. With help of the air, we are cooling the equipment right now. Vignesh, are you there or not? Okay, so if your air is less, so your cooling efficiency of equipment is less, right? You cannot dissipate the heat very easily. So if your cooling efficiency is less, equipment is heated for more time, then equipment performance will also less. Okay, that is the reason that when we increase this installation height, then equipment is derated because of the air density. Because of this, heat cannot be easily dissipate in the environment because air is less available. Okay, Vignesh, hope your concern is clear now. Yeah. So now we are done with this. We are done with this uh, this because GIS is not exposed into the environment, Silpa. So it will be less if impacted compared to the AIS, and that is why in these kind of the things, these kind of the installations, we go with the GIS, not to the AIS. Yes, it will be less impacted in case of GIS because they are not connected with the outer environment. That is the reason. Okay, so I think the view is clear how to read any tender. How to read any tender. I think that understanding is clear to everyone. So step one, take the project. Then step one, take the project. Read out the scope of the work. Step two. Step two is the technical specifications, regulations, ISIN. All this document we need to collect. Then read out the electrical design criteria. That analysis we have done. Then fourth is all the environmental conditions we have to see. All the environmental conditions we have to see, and then these all parameters again we have to read out, that is given in the tender. So I'm not going to review all these documents. So based on the module, based on the point, I will take all the modules. Means when I will come on the switching scheme, then I will discuss about this. When I will come on the cable, then I will discuss about this. When I will come on the PLCC, then I will discuss about that. So all these discussions now we will discuss with respect to the equipment further in the class. Okay. Today, like in the module number one, we have only this much. So I think module number one now we are closing. Study of process involved this bidding to energize study. We discussed all the process. Study of engineering design process, that also we discussed the design process. Discuss how to start designing work and how to study the input tender specification or contract specification. That is point also clear. Study of construction drawing. Construction drawings we have discussed in the day one. What are the construction, what are the document and the construction drawing is required. That again I will take tomorrow. Power system network, that we discuss. Power system network, type of substations why required, that we discuss. All the IC item system that we discuss. Design basis report, yesterday we have seen on design basis report for a wind power plant, that is one in the future. Okay. Electric system design parameters, that also we have seen. The system design parameters, the current, the rated voltage, nominal voltage, impulse, fault current, this all comes into the design parameters. So now we are approaching the module number one, and the next week we will discuss about the module number two, that is the equipment selection and sizing calculations. Okay. Now let me come quickly to this your homework, home assignment review. But yeah, we discuss the fault current, fault current, uh, value selection and the calculations today. And then we discuss about the grid, fault current and equipment current rating. and then discuss about the impact of the installation height and the temperature on the equipment rating. That is the main key learning so far. So coming on this assignment. So let me take one assignment and let us review. So yeah, B is this. So what was the A? A already we have discussed in the class. A we have seen. A we have seen. This A already we have seen. So I have draw here. Now you are coming with the B. Sartaj, are you there? Now can you unmute if you do not have the noise in that case only.
Yes, sir, I'm there.
Okay. So yeah, what you have developed. Let me take you. Established for 225 and 32 kb 2 into 200 MB on 30 by 33 kb 2 into 50 MB services like this. Okay, so this switch is the 220 kb. So we have one line way 1 2 3 4 line way, right? And then let me go to here. This line bay 4 numbers that is matching. ICT bay 2 numbers. ICT bay 2 numbers. So ICT1 and ICT2. And how much voltage, that is 220 by 132 kV right now. So why you put the 220 by 33 kV here?
Yeah, sir, it was a mistake. It was right.
Okay, and the second mistake what you have done here, this
Lines.
lysis. Okay, second mistake, this type of the trafo, it will not be two winding trafo right now. In the class day 1, day 2 we have
Single one,
discussed,
single one.
is
Auto transformer.
it should be
Auto
auto
transformer.
transformer.
ICT
Yes, sir.
transformers.
ICT transformer, yes. The auto transformer in a simple way. Please, if you do not, if you have the noise, then you can mute yourself, Sartaj. Okay. Please, Ganesh, yeah, please mute. Yeah. And then ICT1, ICT2, this much fine that this is 132 kV system. Okay, to ICT bay. What is this line bay? Okay, that is going from 132 kV to the to this is your 220 kV bus, and here your 132 kV bus, this one, and this one line bay where it is going. Line bay it is going to here. What is this? That is not correct.
Okay. Okay, sir.
That is line bay is the line bay, no? Line bay means like that. What I mean to say, let me take if I have one model. Can you see my this screen, this layout? This is one 3D model of the
Yes.
surface station, right? What
Yes,
I'm
sir.
trying to say, what is the line bay? It means this is my line bay. This is transmission tower and this is my line bay. Okay, this is my again line bay. And when I talk about the ICT bay, so this one, this one is my ICT bay. This one here we have put the transformer. This is the area, right? So what you done? Two line bay or four line bay. So this is four line bay. It is coming on the bus. It is coming on the bus that you have indicated here. Indicated here. Two four line bay. Similarly four line bay here. Okay, then ICT 1 and 2. So after the ICT, it will go to the ICT bus here. So that is my 132 kV bus. That this one, and then we have 132 kV line. So this is my 132 kV line here that you can see here. This is 132 kV line. One here and yeah, one even line we have draw here. So this is 132 kV line. So it is not connected to the bus as you have draw. You have connected to the bus right now. So it will go to the
Yes, sir.
line bay.
Okay,
Okay,
directly it will be okay.
it will be a bay just like that, just like it is going here. It is going to the transmission system. Okay, not here, not here. ICT. So line 1, line 2, please take out, and from this is not correct. And then 132 kV. Let me draw for you how we will draw this one. Let me reach. Let me reach. So everyone please follow this discussion and they can recheck their SLD. So I'm not going to check all the SLD. I have taken one SLT, and everyone please correct with this uh, discussion. So two line bay, so one line bay here and second line bay here. It is coming on the 220 kV bus. Okay, this is my 220 kV bus, 220 kV bus, and then we are taking this 220 kV, and then we are stepped down to 132 kV. There is two number trafo. So similarly, we can put two number trafo, and please let me draw as a ICT, not the two winding. That is the one mistake. So what is the symbol of the ICT? I think this kind of the symbols we follow. uh, I'm not able to draw the correct symbol, but I think this kind of the symbols, or you can see the ICT symbol here. How we draw this, like that we draw. Yeah, what is the ICT symbol? Auto transformer symbol. So you please follow AU auto transformer symbol. So please follow this symbol, this one, like that. Is there symbol any draw? This black circle, this some symbol we can draw. Okay. This actually I wanted to draw this much, this symbol. This one like that, then it is going down. So this one please put here. Okay. So yeah. So just let me erase one. So how many pay? How many 220 kV pay? Line by 4 number. Okay, so you correct this 4 number, right now. 4 number you draw here. Line by it is clear to everyone. So 1, 2, 3, 4. Right? Now it is correct. 2 number trafo bay. 2 number trafo bay. 2 number trafo bay. ICT by 2 number. Then it is coming on the 132 kV side. So this is my 220 by 132 kV ICT. Same one this is also. So here I reach on the 132 kV bus. So I can put the breaker here, and then I can draw the 132 kV bus. Now this one here, right? What I mean to say, let me go back here. Go back here. This is my 4 number line way. Yeah, that is my 4 number line way. You forget about this bus bar that I will discuss later on. Just I am representing this RYB, RYB, RYB in a single line only to understand the statement into the diagram. Okay, so 4 line bay, and now if we come to the trafo, again do not consider this three phase 2 line that I will discuss in later stage. So this is going to one bus here. That this bus I am representing at present now by this line. Okay, by this line. And then what about the 132 kV system? How many bay? 132 kV. Okay, future line bay you can draw here. Future ICT, future line bay. Please draw. I'm not going to draw, but you can draw the future bay. I think you have drawn the future bay here also. Future 1, 2, 3 bay you have done. The future scope, yes. Future ICT, yes, you have drawn. This is correct and this is correct. But when it comes to 132 kV system, okay, 132 kV ICT bay, 4 number. 4 number ICT bay. Okay, I'll come on that how 4 number. Line bay 2 numbers. It means there will be 2 number of the ICT line bay. So we'll take 2 number of line bay here. 2 numbers line bay, just draw. Okay, just 2 number line bay draw. And you can put here line 1 and line 2. Similarly, you can put on the top side line 1, 2, 3, 4. Okay, and then again coming back to here, because we have 132 by 33 kV 2 into 50 ampere trafo, then it means this line we will take here, and then I will put the now this will be 2 winding transformer, right? Now because the voltage ratio is greater than 2, so 132 by 33 kV system, again 2 numbers, right? How many numbers here? Yeah, 2 numbers. Okay, so please make this as the 2 trafo, and it is coming now on 33 kilo voltage bus. Okay, Sartaj, now it is coming on 33 kV bus. So 132 kV, how many bay we have? One bay here, right? That is 220 by 132 kV. Second bay of 132 kV ICT bay is here. Two. Third bay is here. Third bay here. And fourth bay of the 132 kV ICT bay is here. So that is why it is coming 4 number. And this 33 kV bus. Now coming to the 33 kV bus. ICT bay 2 numbers. Yes, that we have drawn. 2 number 33 kV ICT bus. This was because this is 132 by 33 kV. So ICT 1 and ICT 2 here. Right? Then how many 33 kV bay? Line bay 6 number. So 6 number of the line bay. 1 and 2, 3, 4, 5, 6. All the 6 number you have drawn here. So coming back, Ganesh Raja, please mute here. Yeah. Okay. So yeah. So this is 132 kV system here. This is clear. Now again we have one trafo that is 1/3 by 33 kV. So we can take this trafo and coming on 33 kV bus. So this is my bus, and now here we have to draw 6 number of the outgoing feeders. 33 kV it will be feeder. So here we have so 2 feeder, but 6 feeder you have to draw. I think now this is clear. Is it okay, Sartaj?
Clear, sir. Clear, sir.
And please, other one, please follow this sketch and please recheck your SLT and you can submit again for the review. And if anyone have developed same, so we can review. Let me take some other Acharya. What you have, what you have developed. Let me see. So I'm not going to review other homework, Sartaj. You correct yourself, then you resubmit.
Yes, sir. Yeah.
Okay, then yeah, you have put all this here. Then 12 page. Okay. Okay, so just those two, and then this two here. What is this? You have taken option number B. Which one is this? That one. Acharya, are you there? Okay, you have put all the symbols here, but that is we will discuss later on. So two number,
Yes, sir.
two number.
No, there
A
were
you have taken, right? A you have taken. A.
there were two reactors, sir, so I put two buses there.
Okay, two bus there. Okay, but that we will discuss later on about that whether we should put two bus like that, because in 400 kV we will follow 1.5 breaker scheme, so that will be the different kind of the structure. So this structure will change, and I will explain that how it will be. Okay,
Yeah.
so please wait. But yeah, you have applied mind that yes will be two bus because two reactor, that is perfect correctly. Yeah, for my 220 kV, that is 220 kV coming here, and this 220 kV base, that is clear. Coming back, coming to the, this is your option number B. So 1 2 line 1 line 2, okay, line 3 line 4, yes, correct. Then this is your 220 by 132 kV ICT bay, that is fine. And okay, and then this is your 132 kV bus here, 132 kV 2 line bay. And then you have taken, where is 33 kV bus? So I think you have taken, where is your 2 132 by 33 kV, this one, okay, right. It is going to where is 33 kV bus? It is going to 33 kV bus right now. 33 kV bus, where is you, this one, you 33, where is the 33 kV bus? Yeah, here,
Yeah, last one.
this one.
Yes, sir. Yes, sir. That is 30 kV
So
buses.
why you connect this 50 MVA two number? So why 80 MVA?
Sir, for future ICTP there is written 80
Okay,
MB.
okay, I got, you have taken the future as per this right now,
Yes, sir.
as per this 50. But future, I think they have asked, also asked only 50 now,
Uh,
where you find
now
80 MB.
I think there is 80, sir.
80, 80.
Okay, 80. Okay.
Down after 30 kV there is written stay for future 130 to 33 1 into 80 MB HD at last, sir.
Yeah, this one.
Yeah.
Okay. Right. So 80 MBA future. Okay, that is 33 kb bus. So where is your 132 kb bay?
And yes, sir. Yes. 132.
This one,
Yes.
right now.
Yeah. Yeah.
All right. All right. Perfect. So yeah, that is going to here. And then this is your 33 kb feeders. So 6 feeder you are going to indicate here, right?
Yes, sir.
Okay, fine. And then I think you understood now. You're following the same practice, Ibrahim. I hope that you understood now.
Yes, sir.
Okay, so yeah, we're going to the next. Raghunath, are you there? We can take you.
Yeah, I'm here. I actually done the substation A only. So
Okay, A I think already we have discussed. Anyway, let us see your drawing. Yeah, that you followed the correct best bar scripts. Correct. Okay, let me see your. Let me show you the line by one, line by two. Okay, and then line with the line reactor, line
all
line.
the others are line future lines with reactors.
There,
Um,
that is mentioned in the tender.
yeah, it is mentioned the space should be considered for line reactor for future lines.
Okay, then two line by here, and then this is your taking. So okay, this is my uh, 1 2 and 3 and okay, this is my ICT 1, ICT 2, bus reactor 1, bus reactor 2. All right, and this is your future ICT both. Okay, that is fine. Okay, line with the line reactor. Let me see where it is mentioned line with the line reactor. That is the one right now. So ICT 2 line by 2, bus reactor 2. Okay, space for the future line by including the space for the switchable line reactor. Correct, correct, correct. Yeah, switchable. What is mean of switchable? Did you understand switchable means?
Yeah, they should include a breaker so that we can take out the line reactor if it is not required.
Yeah, so that will be by one breaker and the isolator breaker and CT will come. Okay,
Yes.
so what is the mistake that you can observe here in your drawing?
Two things is one is I did not include the breaker and I did not include I think the NGR that is required
Correct,
for the
correct,
breaker.
correct. So you have to include, okay, breaker, that is fine, but do not put directly earthing here. You put first NGR and then you go to the earthing. Okay, na?
Got it, yes.
Yes. And before reactor on both sides put the LA.
Uh, yeah, okay.
So breaker, first of all isolator, and then breaker, then CT, then LA, then reactor, and then again LA, and then NGR, and then ground. Okay, Raghunath.
Yeah, got it.
Even though we will discuss these all things in the detail, but you have done some advanced work. So for you, I'm putting my observations. Bus reactor not required the NGR, so that is okay. ICT 1 2, bus reactor 1 and 2 fine. ICT future both 220 kV is okay, correct. Yes, so any this is your 220 kV site, right? Okay, from the 220 kV of ICT, right? So it is main one, main two, and the transfer bus. Okay, and then okay, this is two incomer, and then here we have this TBC, TBC, and here we have the BC bus coupler, and then here we have the line 1 and line 2, two line B. Correct, correct. Future line B you will indicate, and similarly 4. Yes, so that is. I hope you understood about your observations right now.
Yeah, I will add the other equipments. So additional equipments I need to add.
Yeah. Anyway, but because you put the LA reactor here, that is why I ask you to indicate the NGR. Okay. Okay. All right. So you can do one practice for the 220 by 132 by 33 kV also. Okay, Raghunath.
Yeah, definitely.
Yes. And if you are okay, if you understood, then you can make the complete SLD and you can submit us, and I will provide my feedback to you.
Okay, I will do that also.
Complete means how you are going to submit to the client. That in that way, in that
Okay,
say, in that say.
okay.
Okay, so yeah, let me take one more. Silpa, are you able to unmute? Palorji, okay, option B, 1, 2, 3, and 4 line way, correct. This is your symbol is perfect. Yeah, your symbol is perfect. That is the ICT symbol, right? Okay, yeah. So 132 kV. This one, where is the line way? What 132 kV line way is here. Okay, you draw one way, Silpa, are you there? Can you unmute? Uh, oh, can't speak. Okay, Silpa. So I'll tell you what is the best here. Please, this 132 kV feeder do not indicate here. You please take this one as here because there will be double circuit line. So both transmission line will go from same tower. So both line bay should be together. So this line bay, please take here. Okay, you understood now the observations here. Then two ICTs, okay, 80 MB ICTs, okay. Then 33 kV, and this is all size. Yeah, the your SLT is good. That is the one observations. Okay, that is the this line reactor line this bus reactor. One bus already have the reactor. So second bus will come on the second bus, but don't worry, I will explain this kind of the system. Okay, so 4 line bay ICT and 2 line bay, that is fine. And then yeah, same line bay this two, and then future 2 line bay here at TMB. Please line bay put here, and all ICT will put together. So this all ICT will come together. Okay, all the line will come together, and 33 kV bus, 33 kV feeders, that is fine. And then this one. So same observations, all the line will come together. So this line is here. Okay, why I'm telling to all the line will come together, I can show you this one. You can see if uh, yes, you can see here there is my transmission tower. So I will take one circuit from this side, and I will take one circuit from this side. So if I have both the line bed together, then I will use same one tower only. Right now I think this I can show you by one another example. Let me take any side picture. If I have site as built picture, and then we go to here, and that we can see here. Now you can see here RYB 3 phase here, and then RYB 3 phase here. So two line circuit coming from one tower. So that is why both the line, all the line should be together. All the line should be together. This line, like this is correct way, but here also line is, and all the droppers should be together. All right, so this one line by ICT, this is correct. Yeah, this is correct. Yeah, this one is perfect. Yeah. Okay, so this is for your homework. And now let me go to the next. Others, please follow the same discussion for which I could not discuss in the class. Okay, this is submitted by whom? Okay, okay, you got them. Thank you. This is by whom? All right.
Rahmatullah, sir.
Rahmatullah. Yes. Okay. So line bay 400 kV line bay. Okay. Okay. I said bus one, bus two. You have taken the 1.5 breaker scheme. Bus one reactor. That is fine. Line bay two. See both line bay together again. Rahmatullah.
Yes, sir.
Okay. Okay. That is the bus reactor. Bus reactor. Please put along with the ICT. Okay.
Okay.
So we will how to arrange the feeder, that is also one skill. I will explain how to arrange the feeders
Okay.
during the SLT. Line here, all the line together and all the ICT together. So bus 2 here,
Okay,
ICT
sir.
1 and the bus reactor. Why not? Please do not put bus reactor, put the ICT 2 here. Okay,
Okay, sir.
ICT 2 and then reactor 1 and reactor 2 like that. And future line
Okay.
2. Okay, that is okay. Only you have done one right now. So
Two, sir, two.
okay.
DMT I have already done.
Okay, but I received this much, this one page. Okay, no issue.
One page I know, sir. I already sent her another one.
Okay, oh, but DMT already I
DMT
discussed
as
with
well.
the other.
Okay, no problem.
Okay. All right. So we can close today now. You have received the feedback on your home assignment. Second home assignment for this week, I asked yesterday to prepare the insulation table for all the voltage level right now. That study I have given to all of you. Hope you all remember that home assignment. Is remember or not? Yesterday we discussed now to make the electrical design criteria for all the voltage level starting from the LT and up to the ultra, whatever the largest voltage available. Start from the low voltage, go to the largest voltage. Yeah. So let us conclude today's discussion. What is key learning point today? Point number one, what we discussed. We discussed in a layman language why the insulation level, basic insulation level voltage, or why what is the significance of the lightning impulse withstand voltage, switching impulse withstand voltage, and power frequency withstand voltage. That we understood again. Second point, what we discuss, the difference between the since there is a two kind of the project comes. One is the government by the electricity board, and second by the independent power producers company, that is the private company. So between these two projects, what is the difference and how we will proceed? That difference we discussed today, and we learned about that. Third point, what we discuss, that how to select the fault rating, equipment fault rating selection. Am I clear? How to do? And we conclude that for the grid system, do not go on the calculations. If we go for the calculations, let me take just give me 1 second. If I take any rating, let me take the any 220 kV. So I'm going to modify 220, 220, 220 kV here, and then this is suppose 132 kV here, right? 132 kV here. This trafo, let me take 200 MVA as per the project. 200 MVA, 200 MVA. Okay, all this is 30 to 20 kV. Please note down all the things, otherwise might be mistake. Impedance, let me go to the typicals. Okay, 221 32 kV. This one again 220 kV. Short circuit, let me go to the 40 kilo ampere of the this grid, and then 220 by 132 kV, and let us do the fault current calculus. Let us see how much current is coming. Oh, circuit breaker is low voltage, so circuit breaker I have to, this circuit breaker is LV circuit breaker, so I have to delete the circuit breaker. So first come to here, select this, delete this, and then again perform. Yeah. Oh, okay. What about fault current? How much fault current it is coming? 7.1 kilo ampere. That is very less, negligible right now. And how much I have selected? That is 40 kilo ampere. So why a huge difference? Why a huge difference? Because what will happen? This grid will, in 30 years, this grid will increase. In next 30 years, what the load we have connected, that we have not indicated at present, but that load also going to increase. So we are considering not only the present grid rating. Grid means what? Grid means the combination of thousand number of generators, right? Now that comes into the grid. So the number of generator will increase, the number of load growth, the industrial load, the commercial load, the residential load, all the load will increase. So that load will contribute into the fault, that grid will contribute into the fault. So in the 30 or 40 years, whatever equipment I have taken, that should withstand the fault current ratings. So that is why I'm not going with the calculations as 7.1 ampere, I'm going with the 40 kilo ampere. Is that clear? So we discuss here the fault rating selections, and we will not go with the calculus, we will go with the grid regulations, considering the next 30 years, next 30 or 35 years development in the country grid generator, because every years we are adding the solar generations, the wind generations, the thermal generations. Right now, every year the grid is expanding, so that we have to consider, and based on that we will go. So fault rating, not with the calculation, we will go with the grid regulation. That is the one discussion. Fourth point we discussed today, that for the grid substations, the equipment current rating we will go with as per the tender requirement. Because again 30 years margin we have to take. And but when it comes to the power plant, the independent power plant like solar, wind, in that case we'll calculate the current rating as per my installed uh, project capacity, installed project capacity. So in that case we will calculate I, right? So this is the fourth discussion. And then what we discussed, that during the equipment selection, do not only review or do not only consider the electrical parameters, we have to see the environmental condition on which the equipment going to installed. So the site environmental conditions like the seismic zone, the ambient temperature, the mean sea level height, these all parameters also we have to review, and we have to take approval from the equipment supplier that equipment is designed to withstand these all site conditions. And we have done some simulations that if I my installation height increasing 100 meter, in that case there's a 2% drop in the equipment capacity. And why this drop happens? Because the air density, air quantity is less, heat cannot easily dissipate in the environment, so equipment rating will decrease. That is the point. And then we discuss if temperature increase, so every 1% temperature increase will derate equipment around 1%. So that we discuss with help of the heat. Right, this we discuss with help of the ETAP. Fault rating for the industrial, for the industrial we will go as per the calculation, not as per the grid. For industrial, any small plant, right? Fifth and sixth, today we review the homework. We review the homework. Right now, that is the total discussion of today. Right? Any point that is not clear to everyone, please let me know. I will again clarify. Or anything that we miss to list here, let me know. I will add here. Is that fine? Are you all there? And good.
Yes, sir. It's fine, sir.
Okay. All right. Okay. So we close for today. This week home assignment to make the electrical design parameters for all the voltage level. That is the point. And try to make some understanding on that at your end also. Okay. And if anyone facing difficulty, they can discuss with me. Okay, so good night. Now we close for today. Next class is the equipment selection sizing calculations. We will enter now. As now we will discuss as per the project list of drawing and documents. Okay, so we'll see as per the what is the list of document required. We'll go to as per the list of drawing and document. So now we are entering into the designing. This 2-3 class is the introduction and how to read the tender. What is the importance of the parameters? How like this introduction only I just finished. Now I will go to the drawing and documents discussions. Each document discussions. Okay. Next week we'll start that. Okay. So good night all. Thank you. Thank you, Salis. And thanks all for your patience. And thanks for cooperations. Yeah. Thank you.